Haha. Let's do this thing. Are you guys ready for your second type of question? How exciting. Section 6.2. So from here on out, we kind of introduce a new type of question each day. And for each of them, we'll look at, okay, what do we need to be able to do a hypothesis test? And what do we need to do a confidence interval? And but just know that the machinery that we've been working on for hypothesis testing and confidence intervals stays the same. Okay? And there are just kind of some slight alterations depending on the type of question. And so here, oops, the type, I would call this two sample proportions. But if you have a proportion from group 1 and a proportion from group 2, right? What does this this two sample aspect? Well, it means I have an N1 and an N2. Right, I have a sample from group 1 and a sample from group 2, right? It also means that I have some sample proportion from group 1 and sample proportion from group 2, right? And I want to compare these two, right? So we want to learn about, right? We've got these sample proportions, P1 hat, P2 hat. And we want to learn about P1 and P2, specifically how they compare to each other. Oh, hello.
So these package protocols are smarter than before.
Just gonna mute everyone. I don't know what that was. Okay.
Somebody on Tuesdays at once. Imagine.
Oh, why is it okay. Okay. I hope it's okay. I don't know. But we want to learn about P1 and P2 and specifically how they compare, right? Specifically how they compare. What do we know about our null hypothesis? Our null hypothesis, we have to assume that these two things are the same, right? Until we have proof otherwise. Okay? And so that leads us to our null hypothesis on our formula sheet. And big day today, we flip to the next side of the formula sheet. I'm going to grab it all and bring it in here. So from your formula sheet, just as before, you can kind of ignore this. Just like you were working on that central limit theorem lab or not lab, but exercise in Excel, right? We can do the same thing for the difference of two proportions, which is how we're going to compare P1 and P2. Right? We're going to subtract one from the other, and it really doesn't matter which order you do them in, as long as you're consistent throughout the whole problem. Okay? And so what we're going to be building is we're going to build a confidence interval for the difference between P1 and P2. Okay. And just kind of, cruise through this. Okay, looks like a confidence interval, right? Looks like a point estimate plus minus a critical value times the standard error of the estimate, right? And that is what what we've got. The trouble is we're bogged down by all this information from sample 1 and sample 2, but otherwise it looks the same, right? If you kind of ignore anything with a subscript 2 temporarily, right? That looks exactly the same as one sample proportion. Right? You can kind of convince yourself flipping to the front page of your formula sheet, right? And I've got spares if you don't have yours, because it might be nice to have today. Does anyone need one? Okay. Let me know. Okay. So we're just building it out, right? We've got another sample that we need to incorporate. And so it looks the same, except now we're talking about, okay, P1 minus P2, right? P1 represents group 1, of course, and P2 represents group 2. Should have said that earlier, I guess. But everything else stays the same. Okay. Notice that this has the form of a point estimate plus minus a critical value, right? That's your Z star times the standard error of the point estimate. Your best guess at P1 minus P2 is going to be P1 hat minus P2 hat, right? And so that's what makes it the point estimate. And then this huge square root, that's just your standard error of that point estimate. You don't need to memorize that because it's on your formula sheet, but it's nice to know what it is. So we'll be able to build a confidence interval. The interpretation becomes about the difference in the proportions, right? And so 2 sample proportions, we're talking about the difference in proportions. And then we'll move into hypothesis testing. Again, we're going to do hypothesis testing about the difference in the proportions, P1 minus P2, right? How do these two things compare? And for your null hypothesis, I've given you 2 options, right? And that's because I find that this first one is more intuitive, but technically the second one is kind of a more corrector. So they're the same though, right? If you have P1 is equal to P2, if you subtract P2 from both sides, you're left with 0 on the right, right? So they're the same, right? The reason I say it's, you know, it's not more correct, it's just kind of more on the nose, I guess I should say, because then my hypothesis becomes about the difference between P1 and P2. Right? And if I assume that they're the same, which my null hypothesis does always, right? Then the difference between the two would be 0, right? But I find that it's a little bit more intuitive to talk about, okay, I assume that P1 is equal to P2. And then that implies that P1 minus P2 would be 0, right? And so these are equivalent . We assume P1 and P2 are the same until we have proof otherwise, right? So in a way, the calculations are bigger, but in a way, I find that 2 sample proportions are a lot easier to do in terms of setting up your null hypothesis, because remember, in 1 sample proportion, you had to figure out, bless you, you had to figure out which number or what proportion you wanted to compare your sample proportion to, right? And that's kind of difficult sometimes. It takes practice. Okay, whereas here, this is always, hey, this is always your null hypothesis. And one thing that I will say is talking about P1 and P2 just generically like this is not helpful, right? Because if I want to know if there's a difference between the two, right, then I want to know what this 1 is representing and what this 2 is representing. And so I want to see question-specific subscripts here, right? Males and females, PM, PF, for example, right? Dogs and cats, PD, PC, right? Something like that. And just for the null hypothesis. Okay? And so here, first note in red. Red usually means I'll take marks off if you ignore it. Note, we must use question-specific subscripts in H0 and HA. Right, for example, male-female proportions. We would have your null hypothesis is PM is equal to PF, or PM minus PF is equal to 0. I only expect to see one of those, but I want you to see them so that they kind of become ingrained and you can pick whichever one you prefer. Pros and cons to both. Okay. And so you have to have these question-specific subscripts just in your null hypothesis and your alternative hypothesis. Once we get into the test statistic, our step 2, right? It's also going to be a little bit bigger because we have 2 groups that we need to kind of handle. Okay. But we must use question-specific subscripts in your hypotheses. That's step 1 of setting up your of your hypothesis testing. I guess step 0, which we're completely ignoring for a little bit, okay, are the conditions that we need to check, right? And so, and again, it gets a little bit more complicated just because we have 2 groups and we need to check all the groups, right? Or both groups, right? But we basically just do the same thing that we were doing for one sample proportion, just build it out. Now, so step 1, state your null and alternative hypotheses, right? Here it is. And once you've tacked on your question-specific subscripts, then that is your null hypothesis, right? And you can figure out your alternative, right, by just doing the same thing, but changing the sign, right? Not an equal sign anymore. Step 2 is calculate the test statistic. This is a Z. What a relief. Because once we have Z, we know how Z behaves and we can find probabilities associated with Z. Right? We know exactly what Z is, right? It's just the getting there is a little bit more tedious. Okay. What I will say is you can ignore one of these. I tend to only use this first one. Okay. What's the difference between the two? If we look at the numerator, that's the same, right? And then here I have a P hat Q hat on the outside of the brackets. All that's changed here is I've brought the P hat Q hat and distributed it over the N1 and N2, right? So it just depends on how you prefer to do your math, really. I prefer to do it this way, right? because then I can just find 1 over n1 plus 1 over n2, and then I can multiply it by p hat q hat. Right. So I prefer this first one. So that's the one that I'll be using. But, right, you can ignore this if you want. Ignore if you want. Right. And I mean this whole thing. So there's a lot of kind of duplication on the formula sheet, making it look a lot worse than it actually is. And I know what you're thinking. Hold up, Emily. You said P1 hat, P2 hat. We have sample proportions from each group, but then all of a sudden we have a P hat. The heck? Well, P hat. I have it on the formula sheet, where P hat is the pooled proportion estimate. So remember, in hypothesis testing, the standard error for one sample proportion was P naught, right? We assumed that it was centered on this P naught, and then we were able to use that for our standard error. Now, we don't have a P naught because I'm saying, okay, P1 minus P2 is equal to 0. And so what we're going to say is that, okay, if these two things are the same, I should be able to shove both my samples into a pool and then just find a joint proportion, right? And so that's what this pooled proportion estimate is all about. Okay, and so you just say, okay, if they're the same, it doesn't matter. I should be able to throw them all into one group, right? And find the combined number of successes over the combined number of cases. Okay? And that's going to be my P hat. Okay. And then this P hat. And again, I give you many options for finding this pooled proportion. Okay. If you have the number of successes for each group, then that's probably the easiest way to do it. X1 plus X2 over N1 plus N2. If you don't, if you only have the sample size and the sample proportions for each group, then you need to multiply them out. Right. But as long as you remember that it's a combined, well, you don't have to remember it because it's on your formula sheet, right? But as long as you see that it's the combined number of successes, it doesn't matter how you got there. And so these are all the same, right? Wait, I don't know how I close that, but that's okay. Right, notice that these are all equivalent. So just use whichever one you have readily available. There, I guess we're done for today. You know everything you need to know? Nah. But basically, in my mind, because then what? Then what? Once you have your Z, you know how Z behaves, right? Step 3, find the p-value. What's the p-value? Well, it's the probability of seeing a difference as far away from 0, right? Technically, this is minus 0, right? Because my null hypothesis is that P1 minus P2 is equal to 0, right? And I'm seeing how far is my difference from 0, taking into account the standard error, assuming the null hypothesis is true. And so we don't write this usually, the minus 0, but it's technically there. Because our null hypothesis is that P1 minus P2 is equal to 0. And that's why I say, you know, this one is kind of the more thorough way of writing your null hypothesis, because then you have your parameter that you're interested in and what it compares to, which is what we use in our test statistic, right? We take our point estimate, we subtract our null value, right, from our null hypothesis and divide by the standard error. So it's got the same breakdown as before, right? But once we have our Z, then you're on easy street, right? Then you can find your one-sided p-value or your two-sided p-value, depending on your alternative hypothesis. And then once you have your p-value, your conclusion stays the same, right? And so that's why we spent so much time working on those conclusions. If the p-value is small enough, we have enough evidence to reject H naught, or kind of my favorite, if the p is low, then the null hypothesis must go. Pretty cute. I guess it's not cute. I think so. For me, it's silly, but it's catchy, right? And there's been so many times where I'm marking the final exam, and so many margins where it's just kind of scribbled down because it is so catchy, right? And you're like, oh, okay. And then you can kind of use it to, okay, so if the p-value is small enough, then I have enough evidence to reject H naught, right? Is really what it's saying. But it's just kind of a catchphrase, if you will. All right. I know it doesn't feel like it right now, but we'll reach a point a couple of weeks from now, maybe, where if you're doing a hypothesis test and I'm introducing a new type of question, you're going to say, okay, fine. What's my null hypothesis and what's my test statistic? I'll take it from there. Thanks. Right? And so it doesn't feel like it right now, but that's what we're building towards, right? Because that's really all you're going to need to be able to do all these hypothesis tests, right? And so we see a limited number of hypothesis testing questions in this course, but afterwards, right, as long as you feel like, okay, if I know the null hypothesis and I know the test statistic, I can kind of figure it out from there because the behavior is always the same. Okay. Should we tackle the assumptions right away? They're in the slides, but let's just do it. The assumptions for two sample proportions. We already saw it with one sample proportion, right? Where, okay, it depends on if I'm about to do a confidence interval or about to do a hypothesis test. And if I end up doing both, I should check both of them. Okay? And we're gonna have the same scenario for two sample proportions, but also now we have two groups to handle. Yeah. And so the independence condition we build it out, right? Each sample needs to be randomly selected, right? So that we can assume that observations in each sample are independent of each other. Okay. So each sample is randomly selected. Okay. We have the n less than 10% condition, right? And so this one is optional and I'm going to start ignoring it, but technically true. N1 has to be less than 10% of population 1 and N2 has to be less than 10% of population 2. What's not optional is that now that I have two samples, one of the assumptions for being able to use the calculations that we're about to use is that these two samples are independent of each other. Okay. Oops. the samples are independent of each other. This one is new. Okay. There are ways to deal with proportions that are coming from non-independent groups, but that's kind of like a third or potentially fourth course in statistics, and so don't worry about that. But we do have to say, okay, these two things are independent of each other, right? These two groups. Or rather, you argue that they're independent of each other because that's all we know how to deal with. Right. Then we've got our normality condition. And you know what, I'll just add a page. We'll just put this all on a fresh page. It's okay. It's virtual paper. I don't know why I'm so stingy, but I am. I want it to make sense. The normality or the sample size condition, right? This is where it depends on if I'm doing a confidence interval or a hypothesis test. Now, thinking back to a confidence interval, so let's start with a confidence interval. Thinking back to a confidence interval for one sample proportion, right? We had to have at least 10 successes and at least 10 failures, right? Now I have two groups, but that still has to be true for both the groups. Okay. And so we need at least 10 observed successes. In each group, right? In each group. Right. That's the new part. And we need at least 10 observed failures in each group. And maybe I'll do the math here. Right. If you had to do this math, that's the same as x1, which if you don't have the exact number of successes, right, depending on how you got the information, it would be n1 times p1 hat has to be greater than or equal to 10. Right. Depending on what information you have. X2, which is N2 times P2 hat has to be greater than or equal to 10. That's the successes. And then we need at least 10 observed failures in each group, which is going to be, if it's not a success, it's a failure, which is N1 times Q1 hat has to be greater than or equal to 10. Or N2 minus X2, which is N2 times Q2 hat equal to 10. You only have to do one of these, right? Whichever one is easier. And if you like just kind of sticking to one thing always, then I would suggest you use the N1 P1 hat. Because you'll always have to find your p hats. So that's the same, sort of, just built out, right, for two groups. What about a hypothesis test? We need at least 10 expected successes. Now, how we found that expected success before was I had to use P naught, right? From my null hypothesis, I expect to see this many successes, right? And I need to be able to catch at least 10 in order to draw reliable conclusions. So it's still true. We need at least 10 expected successes in each group. And again, right, that's the new aspect. We don't have a null value, right? But we did say, okay, if the null hypothesis is true, that these two groups, they're the same, the proportions are the same, then I shove them all into a pool and I can use the pooled proportion, right? And that would be my null value, right? And so if they're the same, we can use p hat, the pooled proportion. So the math on this looks like n1 times p hat, right? That pooled proportion has to be greater than or equal to 10. No other option here, right? Because it's the expected number of successes. And n2 times p hat has to be greater than or equal to 10. All right, so use p hat, the pooled proportion here. And by that logic, q hat is 1 minus p hat. Because the next component is I need at least 10 expected failures in each group. At least 10 expected failures in each group. And the math on that, if you had to do it, n1 times q hat has to be greater than or equal to 10, and n2 times q hat, oops, hey, it's all jumping around, has to be greater than or equal to 10. That's a lot to memorize, right? And it's going to be worth 1 mark out of probably 8 marks. No, 9 marks, because I also ask you what the question type is for 1 mark. So it's going to be worth the same. And so it's not really worth, you know, committing any of this to memory. But if you need a guide, just like we did for 1 sample proportions, right? Whatever's in your square root, right? P1 hat, that's what you use to check your conditions, right? For a confidence interval versus here in the square root, you've got P hat. So then you use your pooled proportion to check your conditions for a hypothesis test, right? And so it just, whatever you're using in your square root, which is your standard error, that's what you use to check the conditions. Right? And that'll kind of help guide you. But like I said, it's not worth the brain space that it requires. So can tune back in now, I guess. I should have told you that before. Can tune out for this page and then tune back in. All right. Any questions before we do an example? No. Scientists predict that global warming may have big effects on the polar regions within the next 100 years. One of the possible effects is that the northern ice cap may completely melt. Would this bother you a great deal, some, a little, or not at all if it actually happened? So this is a survey that they've asked, and these were the options. Now what they did was they asked, so the general social survey, we've seen it referenced before. It's basically all of the US, it's representing adults in the US. So the general, I think it's a social survey, represents all US adults, or is supposed to. Okay. And so the survey asks the same question. Okay. And so below we have the distributions of responses from the 2010 GSS, as well as from a group of introductory stats students at Duke University. Okay. So they did the same survey with Duke University students. There's a lot of Duke in this textbook because Mina teaches at Duke. Now, because it bothers me a great deal that she then reverses the order, I'm going to swap it right now because you'll see in a little bit how annoying it is. Because later she uses Duke as group 1 and the GSS or the US kind of representative as group 2. But I like to just read them from left to right, and so it's really confusing. This can be group 1, and this is group 2. We have a larger sample in group 2, right? The GSS had a larger sample. In fact, we had 680. Okay. And for Duke, we had a sample of 105. But remember, we're going to check the sample size conditions for both, right? So as long as they're big enough, it doesn't matter. They don't need to be the same or even similar like this. Okay, so let's see. We can compare sample proportions, right, across any of these categories, right? I suspect that we might be considering a great deal a success in this case, right? And then we want to know, is there a difference in these proportions across the two groups? I suspect. Let's read on. It is be bothered a great deal. So she kind of just jumps into it. I don't like that. Let's see here. We want to know, is there a difference in the proportion of Duke students and US adults who answered a great deal? Okay. What we're going to do is we're going to build a confidence interval, and then we're going to do a hypothesis test. Okay. And we can use either of those to answer this question. Okay. And so, should I just do it? Do it on my own. We can answer this question using a confidence interval and or a hypothesis test. Let's do both for practice. Should we get those pesky assumptions out of the way? So we can just move on and actually do the problem. Okay. I'll call it step 0. Check the assumptions. We need to check the independence condition with that new one, right? That the groups have to be independent of each other. And so the independence condition we assume, or I think maybe it says the GSS asks the same question. What do we assume? We assume the GSS was selected randomly, right? And this group of introductory statistics students at Duke University, right, was also randomly selected, or at least they're independent of each other, right? That's an assumption we have to make. Is that time right?
Oh, I wasn't really looking, I'm just kind of.
Well, don't worry, but yeah. Because of the time, 10:45. Yeah, okay, good.
Yeah, that's correct.
Even though for,
Glanced over them. Just, I'm not even really.
don't worry.
You
I
have to
did,
pick up your phone, check the time, then you put it down and you're like, oh, I didn't see that.
yeah, did not register at all. So the independence condition, right? We assume, because it doesn't actually say, we assume both samples were randomly selected. I'm going to skip the 10% condition. Okay. Even though it might be kind of a concern, not for the GSS, but maybe for group 1, the Duke or the introductory stats students at Duke University, right? 105 might be more than 10%, but that's okay. Let's ignore that. Because if we start going down that road, we can't finish the problem, so we ignore it. I guess if we look over time, right, then it would be less than 10%. We assume Duke students and US adults selected are independent of each other. So the independence conditions, they apply to both the confidence interval and the hypothesis test. It's the normality condition or the sample size condition that depends on if we're doing a confidence interval or a hypothesis test.
Would it be incorrect if you stated, like, we assume the GSS and the Duke University tests are independent of each other? Do you have to specify?
We assume that the samples are independent of each other.
Not
Yeah.
the test, okay.
Yeah.
Yeah.
But like I said, way too much brain space for what it's actually going to be worth. So don't sweat it. Just do your best. So for a confidence interval, we need at least 10 observed successes in each group and at least 10 observed failures in each group. Now, here's what I mean by this is nice because I have the observed number of successes in each group. And I can also figure out the observed number of failures, right? I lump all these some, a little, not at all into failures, right? Or 105 minus 69 would get us there as well. Right? And so we need at least 10 observed successes in each group. I have x1, if x1, and you could use xd and xg, kind of question specific subscripts, and maybe that's what I should change it to, right? But xd is 69. D is 69, which is greater than or equal to 10. And xg is 454, which is also greater than or equal to 10. So it's nice to have the actual number of successes, right? But if you don't, if I've only given you the proportions in each group, then you would need to figure out what your number of successes is. Then I need at least 10 observed failures in each group. If my total sample is 105 for group 1, and 69 of them were successes, then the remainder would have to be failures, right? So what I'll do is I'm going to say n duke minus x duke is 105 minus 69. Which is 36, which is small, but it's greater than or equal to 10 still, so that's good. Remember, that's the one that we were concerned about being too small, right? Oh, that Duke sample is kind of small, but it turns out it's large enough to apply the normal distribution. And ng minus xg, 680 minus 454. It's 226, which is of course greater than or equal to 10. This one's kind of bothering me. This you would read the question and figure out, okay, am I about to do a hypothesis test or am I about to do a confidence interval? Right here, we decided we're going to do both. So why not just check all the conditions all at the same time? Right? And then you can see them side by side or kind of next to each other as well. For the hypothesis test, right, we need at least 10 expected successes and failures, and that requires your pooled proportion. So we need to find the pooled proportion. Now from your formula sheet, and maybe I'll grab it from, I'm gonna bump this up. You've got options. So we need to find the pooled proportion, which is the combined number of successes over the combined number of cases. And depending on what information we have, but we just decided that we have this one, right? And so I think that's the easiest way to find what our p hat is. As if we needed more p's, right? This p hat is different from the one sample p hat. And we also have p1 hat, p2 hat. Yikes. P values. I know. But once you get to know all these characters, it's not so bad. Says me, I guess. Easy for me to say. And maybe to try to keep it all on one page here. This is going to be 69 plus 454 over N1, 105 plus N2, 680. 69 plus 454, right? Just shoving them all into the same pile. 105 plus 680 out of 785. So P hat is 523 over 785. 0.666 2420382. I'll round that to, should we be cheeky? 2 decimal places. That is cheeky. A lot, because I don't want to be saying 666 all class. So 0.67, that works better for me. This is what we use, right? Because this is the proportion that we would expect if they were all the same, right? What's a way that we can check in here? That should be between P1 hat and P2 hat, right? We've kind of smushed them together and it should be between those two. We don't have our P1 hat and P2 hat yet, but we could PD hat, so P1 hat or PD hat is 69 over 105. 0.657, which I'll probably shorten up. PG hat, and I rounded already, is 454 out of 680. I'll show that work. 0.668. And our 0.67. Well, it's because I did some weird rounding, right? It's kind of an amalgamation of that. Because this is 3 decimal places versus my 2, this one is actually higher because it was 0.666. So it'll sneak right in there. Right? Looking at these, right? These look similar, right? But we're trying to figure out, once I've taken into account the spread, right? Are they significantly different? But I'll show that work more properly in 1 second. I need at least 10 expected successes, which is going to be in each group. So I have N1 times P hat is 105 times 0.67. If they're all the same, I would expect 70.35 successes in group 1. And in group 2, if they're all the same, times 0.67, I would expect 455.6 successes in group 2. Not terribly surprising to see that those are pretty similar to what we actually saw. Right? Because we also saw that our sample proportions were relatively close to each other. And looks like I need 3 lines, and I've got it. Oh yeah. I also need 10 expected failures in each group. N1 times Q hat 1 minus 0.67 is 0.33. So 105 times 0.33 times 105 is 34.65, which is greater than or equal to 10. I guess I forgot to write it down up here. And N2 Q hat is 680 times 0.33. 224.4 is greater than or equal to 10. Therefore, the conditions for inference are satisfied. How can I just need, I guess, one more line. Therefore, the conditions for inference are satisfied. Whee! Oh, that looks like an evil smiley face. No, you know what? I'm gonna keep it. Hey. Let's start with a confidence interval. Now we're going to build a confidence interval for the difference in the proportions. And so the question might be something like this. Construct should we let loose and make a 90% confidence interval? What? Oh my gosh. A 90% confidence interval? For the difference in proportion proportions of Duke. Technically introductory stat students, but can I just say students? Duke students. Otherwise it gets so long. And US adults who answered. Oops, that doesn't say answered. Who answered a great deal. A great deal to the question would blah, 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 blah. But I'm keeping it as short as I possibly can. Okay. We want to find a confidence interval, right? If I want a confidence interval, I have to ask you, hey, construct a blank % confidence interval for this thing, right? And so that'll be your guide, right? And if I say something like, is there evidence that right? Something, something, then that's gonna be a hypothesis test. But if we're making a confidence interval, then we know, okay, we read our question and we determined already that we have a two sample proportion question, right? But also because I asked you for a confidence interval for the difference in proportions. Either way, puts us here. Which means we need a Z star for our 90% confidence interval. We also need to also work for the P1 hat, P2 hat. We know N1, we know N2. Right? So here we go. P1 hat is going to be the same as the Duke students, PD hat, which was 69 over 105. 69 over 105 is point, and I am going across here, and I know that's bad. Bad. Should be stacking our equal signs, but it would go so far down. Okay. I'll do them side by side instead. 0.65714285571. But let's round this so that PD hat or P1 hat, if you prefer, because my PD looks like 0, but it's supposed to be a D. Now I'm regretting only using 2 decimal places for the pooled proportion. Okay, I'm gonna capture a little bit more. Go to 3 decimal places. Then P2 hat, and notice it's not gonna matter which group you've assigned to group 1 and group 2, but I tend to just, the first one is group 1 and then the second one is group 2. I think it's a lot easier. Yeah. And so PG hat was 454 out of 680. Uh, 0.6676470588. So PG hat, or I guess we could call them US, but GSS is fine too. 0.668 to 3 decimal places. And then recall P hat was 69 plus 454 out of 105 plus 680. And I guess I'll keep the 3 decimal places, even though I said I didn't want to. So annoying. But then I've captured all the activity, so it feels good. We need Z star for a 90% confidence interval. Z star equals something for a 90% confidence interval. Remember how we get there? We're going to use that new table, the T table. I think that's the easiest way to do it. Now you can use the Z table. What would you need to do to use the Z table? You would need to force 90% area in the middle, leaving you 10% split evenly amongst the tails. And then you need to find the Z that has an area to the left of 0.05 or the closest thing. Or I think it's easier to just use the T table, and I'm gonna just zip this up a little bit and say, well, I want a 90% confidence interval. And for that, my Z star is gonna be 1.645. I think that's a little bit easier. And what else? Oh, you know what? We don't need the pooled proportion yet. We will, but I'll add N1, whoops. N1 is 105 and N2 was 680. Now I have all the components that I need. I really flip-flop between D and G and 1 and 2. That's okay. As long as it's not too confusing for you guys. That should be proper. 1, D and G. It's okay. I've got my P1 hat. I've got my P2 hat. I have my Z star. These guys I have already. I have my N1 and N2. So I have all the things that I need. It's just a bigger calculation than before, but let's see how we do. So we want P1 hat minus P2 hat. I'm going to write it out generically first. Plus minus Z star times the square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. Or if we use question specific subscripts, I'm using PD hat as my group 1. Oops. Minus PG hat. So here, whichever group you assign to be group 1, just be consistent about it. And whichever one you assign to be group 2, just be consistent about it. PD hat QD hat over ND plus PG QG hat over NG. That is so annoying to write. So that's why I usually just write the 1s and 2s. But just so you can see the parallels. Remember, the only time that I really care about the question specific subscripts is in your null hypothesis and your alternative hypothesis, right? Because then talking about a generic group 1 and group 2 doesn't make sense anymore. Here, it's okay. All right, so we have 0.657 minus 0.668. Plus minus 1.645 times the square root of 0.657, times 1 minus 0.657 is 0.343 divided by 105 plus 0.668 times 1 minus 0.668 0.332 oops, divided by 680. Slow and steady wins the race here in this calculation. And if you have a store function on your calculator, now's the time to leverage it. Okay. And so what I do is I calculate one component, and then I calculate another component, and then I add them all up. And then I take the square root, and then I multiply by 1.645, right? And then I store that to take it away from that difference. So I'm gonna check in and write out some steps in between here, just because it's our first one, and I want you to be able to look back and follow what we did. But you can skip some of these steps. 0.657, maybe I will do them in orange. Skippable steps. Right, in terms of showing your work. 0.657 minus 0.668 gives me a difference of negative 0.011. 0.657 times 0.343 divided by 105 is 0.002142 plus, and doesn't need that big square root anymore, which I'm gonna store in A. And that store in A thing that I just wrote, that's just for me to remember, and you're welcome to do the same in your work, right? If you have a store function, sometimes you can store it in 1, 2, 3, 4, 5, 6, but I have A, B, C, D, E, F. And then I'll be able to retrieve that full number later on. Next up, 0.668 times 0.332 divided by 680. 0.668 times 0.332 divided by 680 is very small. 0.000, scientific notation, 1, 2, 3, yeah, 3, 2, 6, 1, 4, 1, 1, 7, 6, 5. Which now I keep on the screen and I add store A plus recall A. So I get 1.645 times the square root of 0.002472341176. Now it's possible if your calculator doesn't do scientific notation, you might not get that many decimal places, but that's okay. It'll be there in the background, it just can't show you all of them, right? And so that's the benefit of just storing all these values. Take the square root. If you get crazy weird answers, you probably forgot to take the square root. That's a common mistake. Once I take the square root, 1.645. My standard error for a confidence interval is 0.04972264249. Now, back to not optional anymore. Negative 0.011 plus minus my standard error times 1.645. 0.08179374669. I'm gonna store this in A. It's my go-to. Just make sure that you're done with whatever's in A and then it'll overwrite it, right? So now my interval is going to be negative 0.011 minus 0.08, blah, 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 right? And then on my upper end, right, this is my best guess at the difference from my sample. And then I have my margin of error, which is my buffer around my best guess, and that makes my confidence interval. And so I have negative 0.011 minus that little guy, negative 0.0927937469 up to negative 0.011 plus that little guy 0.07079374669. We can trim this up now, right? And just use rounded values. Or negative 0.09, let's do 3 up to 0.071, 3 decimal places. Remembering that this is the difference in the proportions, right? So now I'm 90% confident that the difference in proportions is somewhere between negative 0.093 and positive 0.71, which also, or 0.071, which also tells me that 0 is an option, right? This interval crosses 0. And so this means that later, I suspect I'm not going to have enough evidence to reject H0. Right? Because I'm 90% confident that a difference of 0 is in there somewhere. So here, notice 0 is in this interval. That's more for later. All that work for only half the marks. Because what's the other half of the marks? We have to interpret our confidence interval. But we know how that starts. Okay, so let's see here. We are 90% confident because I made a 90% confidence interval. We are 90% confident the interval from negative 0.093 to 0.071 captures. Here's where we're into kind of foreign territory a little bit, although not really, because we're just going to grab whatever the question was asking for, right? Build a 90% confidence interval for, and now we have built it, and now we're 90% confident that this interval captures the difference in proportion of Duke students and US adults who answered a great deal. And no, it doesn't need to be beautiful, clearly. Captures the difference in proportions. Can I be lazy? Difference in proportions of Duke students and US adults. The quotes moved to be around US adults, which is kind of funny. And US adults who answered a great deal. Was that quicker than just writing it up? Probably not. the key is that this is for the difference in the proportions, right? And so, right, but the question will ask you, hey, build a confidence interval for the difference in the proportions. So it's not that big of a stretch, but then when we're interpreting it, right, we have to think about, okay, well, this is the difference in the proportions, P1 minus P2, right? We're 90% confident that the overall population proportion, difference in population proportions is somewhere in here, right? And so for later, right, we see that a difference of 0 is in this interval. How about for a hypothesis test? What would that look like? Is there evidence? Right, usually if I ask, you know, is there evidence that this, that means it's a hypothesis test. Is there evidence that there is a difference in proportions of Duke students and US adults who answered a great deal? We can go with a gut reaction. Okay. From the confidence interval, right? We saw that 0 is in the interval, right? We saw 0 is in the interval, so a difference of 0 is a reasonable outcome. Is in the interval. So we suspect we will not have enough evidence to reject H0, right? We already checked the conditions, so we're going to jump right in, right? And state our null and alternative hypothesis, right? Because this interval, just to highlight what I mean here, is now we're talking about how P1 minus P2 behaves. So on this number line, and we found that it was between negative 0.093 and 0.071. Well, 0 is somewhere in that interval, not necessarily at the center, right? But maybe I'll shove it over a little bit. Otherwise, it looks like I centered it on 0, right? But 0 isn't in this interval on this number line, right? Which tells me, okay, I'm probably not going to reject H0. But let's see here. Step 1. State the hypotheses. That's something we know how to do, or we've worked on it a lot. I worked hard at it. And from our formula sheet, we've got the clues. If you work with the formula sheet instead of against the formula sheet, it's got all the clues. This is where I need you to make question-specific subscripts, right? And so our null hypothesis is that either that PD is equal to PG or PUS or whatever you want to, but I've been using G, so, right? That's nice and clean. I assume that they are the same. Now, Is there evidence that there's a difference in the proportions? That's where it gets boggy, because we're going to talk about the difference in proportions being different from 0. Oy. Okay. Or if I want to know if there's a difference, right, PD is not equal to PG, because I want to know if there's a difference. That's a little bit cleaner. And that's why I say this one is a little bit more intuitive, right? Versus, right, or P1, oops, I should do PD minus PG is equal to 0 versus my alternative hypothesis that PD minus PG is not equal to 0, right? The difference in proportions is significantly different from 0. Oy. I think this one's a little bit cleaner, right? Nicer to look at. But choose your own adventure. Pick one that you like and stick with it, and just ignore the other one. Right? Later, we'll need to remember if we have a one-sided test or a two-sided test. These should have the same sign, right? And so this is a two-sided test because I'm concerned with either extreme, right? If PD is greater than PG, that's a concern. And if PD is less than PG, that's also a concern, right? So this makes it a two-sided test. I'm going to grab that sample information. That we had earlier, including our p-hats. Or including our copy. Pooled proportion. Jot down everything that we need. All right, this is our pooled proportion. Now we're ready for step 2. Do the test. Or calculate the test statistic. The reason I say that all the time now is because I used to only say do the test because I thought it was catchier. But then I had a lot of students asking me, well, it's asking for the test statistic. I don't know what that is. So now I feel like I have to call it what it is. All right. What's our test statistic? It's the next thing on our formula sheet, right? And again, I give you options, but I'll be ignoring the second one, right? I'm going to use this version. And technically, Z is the difference in P1 hat minus P2 hat minus our hypothesized difference P1 minus P2. But because this is always 0, it's going to go away. So we don't even bother writing it out. You don't need to know that, but that's where it's gone. So it does have the same structure of a point estimate. How far is it from my null hypothesized value, taking into account the spread from the null hypothesis. So here we go. We've got all our P's, and this is where I don't bother writing question specific subscripts, even though it's only a couple of spots here. but we'll just jump in. 0.657 minus 0.668 divided by 0.666 times 1 minus 0.666 is 0.334 times 1 over 105 plus 1 over 680. Just plugging in those values. Now, like I said, I like to simplify each of these fractions first, add them up. And I'll do the same thing here. These are skippable steps are in orange. Here we go. 0.657 minus 0.668 is still that difference of negative 0.011. Let's see here. 1 over 105, let's start there. 0.666 times 0.334 times 0.0095238. I'm going to store that. Plus 0.00147058. It keeps going, but once I add that to what I stored in A, I get negative point, oy, too many decimals. 0.666 times 0.334 times 0.01099439776. Don't forget that square root. Gonna make a real mess if you do. Times it by 0.334 times 0.666. Square root of 0.0024456378815. Now, back to what I need to see is this square root. 0.04945339033. Notice that that's very similar to what we found in the confidence interval, but not exactly the same, right? And that just, it just lends itself to, okay, I'm probably not going to reject H naught because these are so similar. And negative 0.011 divided by that guy, I find a Z of negative 0.22243166. Using the Z table, you know how to find the p-value for this thing, but what I'm also trying to get you to start doing is to use the Z or the T table instead, right? Just to have it match the procedure later on. So step 3 is find the p-value. If you want to visualize it, right, Z is centered on 0. And we found a Z very close to 0, negative 0.222. And the one-sided p-value is going to be very large, right? I expect. But we want a two-sided p-value, right? We'd be just as concerned if this 0.222 happened on the upper end. you know how to find these two areas, right? These two combined areas using the Z table. Right? You can find a Z of negative 0.22 and find the area to the left and multiply it by 2. You can do that. But using the T table, which we haven't had a ton of practice with, we find that the absolute value of Z equal to negative 0.222, let's say 4, is going to be between two values. Right? The absolute value drops the negative. And just going to go grab this here, copy. So down here, I try to place my absolute value of Z somewhere on this line. Now, this is another one of those scenarios where we end up over here, right? But we know it's going to be very, very close to 0. So that makes sense. So all we can say is that Z is somewhere between 0 and 0.674. Right? Which makes our two-sided p-value, or two-sided p, matching the table, how they've said it, right? One-sided p or two-sided p. We said we had a two-sided test, right? I care about both extremes. And so my two-sided p is going to be somewhere between 0.5 and 1. Womp womp. Drawing this out, right, sketching this out means that, okay, I'm not actually that shocked by my finding, right, that my p-value is huge, huge. Right? My one-sided p, the area in one of the tails is going to be between 0.5 and 0.25, right, 0.5 in the center, and 0.25 at 0.6 or negative 0.674. That's all it's saying. And then I multiply it by 2. So my p-value is huge. Step 4 is our conclusion. Same 3 parts, right? You say what your p-value is if it's less than or not less than the alpha level. Yeah. We can use an alpha level of 0.1 to match our 90% confidence interval. Why does that match our 90% confidence interval? Because if I have 90% here, then I have 10% left over for a two-sided test, right? Then my alpha would be 0.1. If you want to use 0.05, that's fine too. Either way, we're not going to reject H0 because our p-value is huge. So we say since our two-sided p-value, right? Give me all the information that you've worked so hard to get, right? You know that you needed a two-sided test and you know what your p-value is, or at least a range for it is between 0.5 and 1. It is not less than our alpha level of 0.10. That's just to match the 90% confidence interval. Right, if you wanted to use 0.05, it's still not less than 0.05, right? That's smaller. Which would match what confidence interval? A 95% confidence interval, right? So your conclusions are going to match depending on what your alpha and what your confidence interval are. This only works for two-sided tests, but I'm getting ahead of myself. For one-sided tests, you'd have to multiply it by 2. It's not less than our alpha level of 0.1, which means we do not have enough evidence to reject H naught. Therefore, good time too. Last part. Copy. You reword the question as an answer. There is evidence. Is there evidence? Well, turns in there is not evidence. I tried to bung that up, didn't I? There is not evidence. I'll have to do it piecemeal here. That there's a difference in proportions of Duke students. Proportions of Duke students and US adults who answered a great deal. Period. Right, which matches what we found with our confidence interval. Nice. See? Not terrible. Can do a confidence interval, hypothesis test, and the rest of the slides really, truly just do exactly all the things that we did. Found a confidence interval. I think they did a 95% confidence interval, right? Everything else stays the same. Hypothesis test. Assumptions, pooled proportions, and a recap of the assumptions. You did it. Now, gearing up for Friday, we're going to do chi-square goodness of fit testing. Just kind of funny to say, but it's a technical name for it. So the chi-squared introduces a new test statistic, which is the chi-squared. So that's hard, but what's nice is we only do hypothesis testing for chi-squared, so no confidence intervals. And so you can gear up for that for Friday. If you have any questions, let me know. Otherwise, I'll see you then.